You know what? I'm gonna steal the mic over there. We don't need two cues. All right. Welcome, everyone. I'm Don Porter from UNC Chapel Hill. I'll be chairing this session. Thank you all for making the long, arcane, and toilsome journey out to the fairway for what will doubtlessly be the most exciting session that everyone will speak about as an underground sensation for years to come. So our first speaker is Massimo Giordano. He's a recent graduate from Stanford who's now working at Tesla. And he's going to be telling us about TinyForge. So with no further ado, take it away.
Thank you. Thank you so much for the kind introduction. And I will go straight away talking about TinyForge, our work on a design space exploration, aiming to improve energy and silicon area, specifically for tinyML computer architecture. And I will describe the role of the custom latch array that we introduce. So a little bit of introduction on how do we go from the cloud computing that consumes hundreds of kilowatts of power down to consumer electronics that consumes only hundreds of milliwatt, but then down to the Internet of Things that is really constrained by power because it needs to last long days, sometimes years, on a small battery. So you really have to consume only in the order of microwatt of power. And today Works will focus on this topic, Internet of Things. So the trade-off here are interesting because I could use a commodity MCU that consume more power and just put a bigger battery, right? Or I can design a fancy custom accelerator, energy efficient. It's going to be larger inherently and just put a smaller battery, but it's going to be too expensive. So we really need to optimize both so that we can be both small area and low energy per inference. So the compute architectures are mainly dominated by memory, the memory hierarchy, and the data movement within the chip. So we see here the memory hierarchy and the data movement is mainly determined by the size of the memory. Bigger memory means fewer tiles, fewer memory access, and similarly with the size of the parallelism. Bigger compute array means fewer access as well. And we have a trade-off here because we wanted the higher level of the memory hierarchy, bigger memories, very dense, so that they can store all the activation and weights. And closer to the compute, we need low energy memory that inherently will be bigger. And so let's understand what are the trade-off here. So if we take a large SRAM, we'll achieve high density and we'll have a large sense amplifier to be able to detect the signal of the bit cells. So high energy, high density. And when we try to bank it with small banks, we see that the overhead of the analog sense amplifier is kind of constant. So the density drops significantly and the energy doesn't improve. So if you really want low energy memory, you need to use latch array, synthesized latch array. However, they're very large because they have a lot of transistor. They have a digital readout as a max. So ideally, we really want a low energy, high density memory. And for this reason, we introduce a new type of memory, a custom latch array. We invented and introduced this new memory that we made a tape out and validated in actual silicon, and is really a hybrid between an SRAM and a latch array. So we have the bit cell driving the output, but instead of a digital max, as a synthesized latch array uses, we have an analog max, similar to an SRAM. These allow us to achieve extremely low read energy, 60 times lower than an SRAM and 5 times lower than a synthesized latch array, in the order of 11 femtojoule per byte. Again, those are measured in real silicon. And so I want to emphasize how such a low energy, read energy, is almost like having a memory that is free to read. And let me explain what I mean here. 11 femtojoule is about 8 times lower than a multiply and accumulate in 8-bit. So it doesn't really matter if you access it for every multiply. So we can leverage that, and here is I will describe how we do that. So a little bit of background on how data flow works. So if we have a compute array and a memory hierarchy, we have to tile the input and the weights in a way that we can perform all the operation of the compute array. So the key here is that if we use a denser memory and smaller compute elements, we can have bigger compute array and therefore accessing this tile a fewer number of times. We can make a step even farther and have enough memory next to the compute element to be able to store the entire weights of the DNN next to the compute element. Now, so this avoids having to load the weights from main memory to the compute elements. But if accessing this memory is extremely low energy, we can actually get rid of the buffers because we can load an input from main memory, loop through all the weights that need the input, and move forward to the next input. So without having to reaccess it multiple times. That allows us to get rid of the buffering and save area and energy. So now the question that we wanted to answer is this interesting architecture just in the same Pareto curve of existing architecture, just at different design points, so larger, lower energy, or is actually a better Pareto curve? Are we improving state of the art, or is just different point in the current Pareto curve? So to answer this question, we are comparing different memory hierarchy from storing all the weights off chip, and we call that OCM on top, or storing all the weights in main memory on SRAM, or storing all the weights interleaved with the compute elements. So those are the 3 memory hierarchy that we will investigate. And then we build a parameterized template. This is a parameterized computer architecture. We can define the size of the memory, the size of the compute parallelism, differentiating between systolic and combinational, and how much memory do we have within the P. So now we have this design flow where we can start from arbitrary configuration with the random size of memory and compute and so on. And then we use value that we extrapolated from synthesis run of a large variety of configuration of the hardware components. And this will allow us to estimate the area and power of this specific architecture. So, but we are interested in end-to-end performance, so energy and latency. We don't really care about per se the power and the throughput, but we need to obtain energy and latency value. To do so, we use Zigzag, which is an open source framework to map a workload on specific architecture. So we can, from using Zigzag, we can actually calculate the number of memory accesses and estimate energy and latency. So this will be a point in this space, and we can run this algorithm based on a genetic sorting, so that over multiple iteration, it will find the Pareto curve. And so in about 1,000 iteration, you can see here in gray are all the point that has been explored, and in gray is the final Pareto curve that was found. And then we can explore each configuration to understand memory accesses and resource utilization and the data flow. So now let's take a step back and look at the results and understanding the impact of different memory hierarchy. So if we store all the weights of chip, we see that we are completely memory bound. Most of the energy comes from reading the weight from off chip. So it doesn't really make sense to try to optimize anything else. Why using fancy low power multiplier when most of the energy is from bringing the weight from off chip. So then the next step would be, okay, let's keep all the weights on chip in SRAM. And we can see here where custom compute start improving and is no longer memory bound, it start becoming compute bound. And so we can improve the compute to further lower the energy per inference. So now let's understand what is the impact of storing all the weights next to the compute elements. And let's start from using conventional synthesized latch array that you can just put in your digital flow. And you see that you suffer from a large area overhead, and that actually does not improve the energy per inference. And that's because the accessing this memory is still too expensive. So we cannot leverage new data flow. But when instead we use custom latch array that are just 11 femtojoule per byte to access, we can change the data flow, get rid of the buffers, and we can see that we can lower the energy and reduce the area overhead. Finally, we look at how we can take the same technology and apply to larger model, such as a transformer. In this case, we look at TinyBird because we're still interested in deploying these in embedded system, where you see here that the models are significantly larger for an IoT that need to run continuously. And so here, storing all the weights in this custom latch array is still prohibitive because of the lower density that the custom latch array have. So we propose an approach where we still store all the DNN weights in the main memory, but at every layer, we load an entire layer into the compute array. And this will still allow us to avoid the data buffer because for every input, we can loop through all the weights of the layer till we finish the entire layer. And we show that this approach allows us to strictly be better than conventional approach, which are storing all the weights in SRAM and buffer the data from this SRAM and achieve better energy and silicon area trade-off. So just to conclude, the main takeaway of this work is that our custom latch array allows to store all the DNN weights next to the compute elements. They're extremely low energy to access, 11 femtojoule per byte, which is about, again, 5 times lower than synthesized latch array and 60 times lower than SRAM, achieving close to SRAM density. And this allows us to explore new data flow, like get rid of the buffers, and improve energy and silicon area trade-off. And finally, we explore how we can use this memory for larger model, such as tiny transformers, and improve the trade-off in this computer architecture. So with this, I conclude my talk, and I'm happy to take any question. Thank you so much.
All right, any questions? I'd encourage Chen to go ahead and start setting up while we do this.
Do you think you can expand a little bit on the analog?
Say your name and where you're from.
Sorry, I'm Riss from UC Santa Barbara. Can you expand a little bit more on the analog multiplexing the custom latch array does to achieve the energy efficiency?
Yeah, absolutely. So when we look at a custom digital array, like a synthesized latch array, you see that you have a latch, and then you have a digital multiplex, and is digital because it needs to be able to be synthesized in the digital flow. And so you cannot short transistors in a digital flow. But if you go in and you make a custom macro, you can actually do what SRAM do, where you connect multiple input on the same wire. You're literally shorting them, right? LVS will complain a ton if you would do that, but you know what you're doing. You can do it if you have a control logic that activate only one word at a time. So by combining these two methodology, SRAM topology, SRAM readout, but having similar to a latch array where each bit cell drives the output, we were able to significantly reduce the read energy.
Yeah, That's very interesting. Thank you.
Thank you.
All right, let's thank our speaker one more time.
Thank you so much.
All right, our next speaker is Zishen Wen. He's a fourth-year PhD student at Georgia Tech, and we'll be hearing about how to deal with bit errors in autonomous systems. So thank you.
Yeah, thanks, Dan, for the kind introduction, and thank you everyone for working for a long distance to attend our session. So I'm Zishen from Georgia Tech, and it's my great honor to be here today to present our work, MulBERRY, enabling bit error robustness for energy-efficient multi-agent autonomous systems. So through this talk, we will understand the challenge of building efficient and resilient swarm autonomous systems, and also to optimize the efficiency, performance, resilience of this swarm intelligence via this cross-layer co-design approach. So as a motivation, I want to share some of my perspective of these autonomous machines. So as we all know, these various swarm intelligence, such as drones, cars, robots, are on the rise. And to unlock their potential, so we have been proposing techniques to improve the mission performance, efficiency, and resilience. And all these aspects are important, and many times they correlate with each other. So it's extremely important to co-optimize this aspect. So how to achieve that? And just to keep everyone on the same page, so what is autonomous machine computing? So take drone as an example, which is also this work will focus. So from sensing to actuations, typically there's two types of paradigms. So one is the classical perception, planning, control, this a kernel-based method. And another is this end-to-end learning-based method, where the neural network will directly generate the action based on the sensing through some reinforcement learning approach. And then for this multi-agent or the swarm autonomous systems, so agent will interact with the environment through their own data and will jointly learn a unified model to achieve the defined goals. And this agent will communicate with the servers about their model without sharing their local data typically. However, building these systems and to achieve the high performance efficiencies face several challenges. So the first is the strict resource budget. To achieve these fully autonomous applications, so the drones need to run some complex algorithm on board. However, these safety critical drones are usually size, weight, and power constrained. Here are these three types of drones as examples, and you can see they have limited onboard batteries, endurance, and flight weight. So it becomes imperative to achieve this energy efficient computing for that. So people have proposed, several software and hardware techniques such as quantization and optimized data flows. And actually another method that is orthogonal, which also means can be applied in conjunction with the other method, is we can lower the supply voltage, especially given the quadratic relation between the energy and voltage. So here you can see the plot on the right showing the energy will decrease when we lower the voltage. So a second challenge is the complex compute mechanical correlations. So different from the other mobile applications, drones have many compute and mechanical components. And actually the compute power is only a small fraction of the total power, with the majority of being used for the flight motion. So the question here is, will optimized compute will really bring the system level benefits? And the third challenge is, although scaling down the voltage can reduce energy consumption, as we just see here, it will also result in some memory bit failures. So here we characterize the bit error patterns from a 40 nanometer SRAM chips, and you can see in the plot of the of this red curve of the right y-axis. So the bit error rate will exponentially increase as the voltage reduce. And the plot on both the left and right side are our profiled result on the other chips. So you can see that the error patterns are different across different devices, and some are more random distributed, and some have more column aligned patterns. So the question we are asking in this work and trying to solve is, how can we achieve this aggressive energy savings under low voltage operations, yet remain computationally resilient for this swarm autonomous systems. So to achieve that, we propose like MulBERRY framework, basically to co-optimize the performance, efficiency, and reliability. So like MulBERRY framework includes 3 steps. So the first is through some of the drones system categorizations to provide us some insight. And second is we propose this efficient and robust swarm design. And finally, we will deploy that on the different application scenarios. First, let's go through some system categorization insight. So if you remember the challenge we just talked about, so in this drone-like system, compute and mechanical, they will correlate with each other. And here is we find that although the compute power is only a small portion, but it actually has a huge impact from the system level. So why is that? Let's look at this analysis on the right side. So say we do this low voltage operations. So scaling the voltage down will actually reduce the payload weight. So why is that? Because this low voltage will reduce the peak temperature of the systems, thus can reduce the required size and weight of the heat sink through this thermal analysis. And this reduction in this payload will translate to this improved safe flight accelerations and also the safe flight velocity. And if the drone can fly faster, then that means to finish a task, say from point A to the point B, if the drone can fly faster, the drone can reach the destination in a shorter time, which means it can reduce the flight time and also the flight energy. And with the lower the flight energy for single missions, then that means under a single battery support, the drone can finish the more number of successful missions. So a small reduction in this power, in this compute power, will impact this flight speed, thus resulting in this significant energy savings from the whole end-to-end drone perspective. Now we have this insight that these low voltage operations can only benefit this compute energy, but also bring system system level mission benefits. Next, I will present our efficient and robust swarm system design. So the key design principle here of this MulBERRY is a cross-layered robust learning framework that integrates the algorithm level error-aware learning with system level collaborative server agent collaborative and this hardware level thermal voltage adaptive adjustment. And the goal here is to achieve this aggressive energy savings and a low voltage operation is computationally resilient for the swarm autonomous systems. And this is the proposed MulBERRY system design, which consists of a bag of the optimizations. So the first key technique is this 2-stage swarm robust learning, where we first conduct this offline learning with injected random bit flips under this normal voltage. And then we deploy the offline learned policy on device and enable each drones to continue learning a robust policy on this low voltage device that incur errors, and then perform this navigation task on the same hardware. So through that, we can achieve this robustness, efficiency, and quality of flight improvement. And here I will briefly show the algorithm block of the MulBERRY framework. So we'll start from initializing the swarm autonomous navigation policy. And the goal here is to learn a robust model through this multi-agent reinforcement learning. And each agent, each drone will perform this robust learning in parallel, will periodically communicate with the server. So how to achieve this error-aware learning? So first we will inject this bit errors in the policy ways. So the random distribution is generated using the voltage bit error rate curve from our memory categorization. And then we will compute these Q values, loss, and gradients based on the perturbed ways. And the robust learning in the MulBERRY is designed to work in both error-free and faulty hardware. So we use a average of the clean and perturbed ways in this gradient update. And for the details of this algorithm, please refer to the paper. And the second key technique is the low voltage payload optimization. So inspired by our previous system categorization insight. So under this low voltage operations, we can reduce the heat sink size, thus the drone payload. So this can lead to the increased acceleration and the flight velocity. Thus can reduce the mission time and mission energy. So we'll leverage that in this MulBERRY framework. And to make sure the system performs well under this low voltage and smaller heat sink payload, so we propose this collaborative sprint or slack operation. So this idea is inspired by the computational sprinting in the mobile processor domain. So basically the drones can alternatively operate at nominal voltage, which is the sprint mode, or the low voltage, which is the slack mode. So like say like when all the agents are sprint, which means they operate at low voltage, so the flight time is slower, but the when all of the drones are operate at the like sprint mode, then they means they operate at the normal voltage. So the flight time is lower, but the flight energy will increase due to their increased power, and also the peak temperature may exceed the designed thermal limit. And on the other side, when all the agents, they are slack, which means they operate at low voltage. So although the thermal constraint can satisfy, the model may not converge due to some bit errors and result in the low performance. And here's a snapshot of our thermal analysis of this sprint or slack mode. So you can see that on the x-axis is a fraction of the period of which the drone is the printing, which means the sprinting duty cycle. And on the y-axis is the peak temperature of this. We use the RISC-V processor. So you can see that when the drones are always sprinting, so the peak temperature is pretty high. And when the drones are always slack, so we can see the peak temperature is lower. So leverage that, we propose this collaborative sprint or slack operations. So each agent, they will sprinting for a few short time steps in a round-robin fashion. So in that case, the model can converge well, which means the successful rate is higher. And also the commutation can stay within the thermal limit, which means we can reduce the payload and overall flight energy is lower. And last is last technique. This is adaptive swarm knowledge sharing between the agent and server. So basically the communication intervals and the model weighted factors can be adaptively adjusted using different scenarios. So for more details of these techniques, please refer to our paper. And finally, let's see some deployment and evaluation results of the MulBERRY framework. So we use the drone simulation platforms integrated with this Unreal Engine and this AirSim to evaluate mobile framework. So the Unreal Engine can model this realistic environment, and AirSim can model this drone dynamics. And it will adapt this collaborative autonomous navigation task where the drones are initialized at the start location and they navigate across the environment to reach the destination without colliding with the obstacles. And we test different sizes of the drone swarms from 4 to 12. And we configure 2 drone platforms. One is the nano drone Quiz Fly, and another is the micro drone DJI Shadow with the different sizes. And each drone equips with a 4 RISC-V rocket core with on-chip SRAM caches. And for the evaluation metrics, we evaluate both the compute level efficiency and mission level metrics, such as the flight mission successful rate, flight time, energy, and the number of the completed missions. And the first is this robustness improvement. So just remind you that the one challenge of this low voltage operation is it will result in the bit errors. So the MulBERRY can increase the task successful rate under this low voltage operation. And as a result, the average flight distance for a task of this autonomous navigation is also lower due to this optimal planned trajectory of this robust model. And we further evaluate the energy of each mission and the number of completed missions under this battery support. So this is the MulBERRY with just error learning. And adding this low voltage payload optimization can reduce the flight energy. And with this collaborative sprint or slack, the drones can safely operate at even lower voltage, thus further lower this mission energy. And this adaptive knowledge sharing can further bring the benefits. So compared with the baseline, this nominal voltage operations, so MulBERRY can enable this safe low voltage operation with around 90% less flight energy and 22% more completed missions. And we further evaluate this MulBERRY across the voltage and chips because we find that chips on different drones can have the different error patterns. And we evaluate the successful rate and flight energy in these different scenarios. And observe that the MulBERRY is scalable across different voltage and chip error patterns and consistently improve the efficiency and robustness. And we also evaluate that on the different environment of the different obstacle densities and measure the flight energy and number of completed missions. And we observe that the MulBERRY is adaptive across different environments and can improve the efficiency. Particularly, we find this sparse obstacle environment can enable the lower operating voltage. Furthermore, we evaluate the MulBERRY across different drones and models of the different sizes, and find that it's adaptive across these drones and models, and improve the efficiency and robustness. And also we find that MulBERRY can enable the more mission energy savings under the smaller UAVs and its larger models. And to summarize, we conduct in this work, we conduct the drone system characterizations and then propose this efficient and robust swarm system design and evaluate across the different scenarios of this design. And through that, we achieve this aggressive energy savings and this low voltage operations. It remains computational resilient for swarm autonomous systems. So with that, I will conclude my talk. Thank you for your attention, and I'm happy to answer any questions.
All right, let's thank our speaker. We can maybe squeeze in one really quick question, but we're a little slightly behind. So I think I'd like to go ahead and ask the next speaker to come up. Sorry about that. You go ahead. Yeah, shoot.
Hey, so thanks for the talk. Do you guys have any numbers on how much lighter you can make the drones by reducing the heat sink size when you operate at lower voltages?
Sorry,
So yeah, I had the same question.
Sorry?
I was curious about the same thing.
So you're reducing heat sink size because you're operating at lower voltages,
Yeah.
and that in turn makes the drone lighter. How much lighter can you make the drones? What's the kind of weight reduction that you get?
Yeah, that's a great point. So I would say it depends on the size of the drones and the size of the models. So usually the smaller size of the drones and larger of the models, we can achieve more heat sink size reduction. So say for this Kshitij fly is the 27 grams of the drones, and if we use the 5-layer policy, remember can reduce the heat sink size by around 20 to 30%. Yeah.
Very cool.
And
Thank
we
you.
provide the detailed data in the paper. You can check it.
Great. Let's thank our speaker one more time. All right, our third speaker is Nisarg Ujjankar, who is, well, I've already forgotten where you're from. At Rochester, my apologies. I got a little distracted there. So with no further ado, let him get into telling us about how we're going to leverage color discrimination for efficient image encoding.
Okay. So before we talk about image encoding, let's first take a look at the mobile SoCs. So as a matter of fact, you'll see that the memory traffic actually accounts for more energy consumption than compute itself, which is an even bigger problem for emerging mobile platforms like the virtual reality devices. Now, to give an immersive experience, these devices have to support a wide field of view. This comes at a cost of transmitting more data between the CPU and the memory than your typical smartphones. Now, the canonical way to reduce data traffic is through compression. And so in this work, I'm going to present a novel frame buffer compression scheme that leverages human color perception to get better compression rates. Here's how the rest of the talk is going to be organized. First, I'll talk about human color perception, then perception-driven frame buffer compression, and then I'll talk about the results. Now, a key insight from human visual perception is that the acuity of in your periphery of the vision is quite low. For example, if you hold your thumb out in front of you and fixate on it, you can't really tell what's going on in the periphery that accurately. And as it so happens, most of the pixels in a VR environment actually fall in the periphery of the vision. And because most of what I'm going to talk about my work depends on where the light actually falls on the retina, let me quickly introduce this notion of eccentricity. So we define the foveated region or the center of your retina as having eccentricity of 0 degrees, and all the other points as having eccentricity greater than 0 as angular distance away from the foveated region. Now, a consequence of low visual acuity is that humans can't discriminate between different colors that effectively. For example, if you look at these 4 color tiles, they have different sRGB values, but most users wouldn't really be able to tell the difference between them. Now, this inspires our compression algorithm because we don't need to encode these 4 different colors using different bit streams. But we want to do the compression in a systematic way. So the scientific question here is that for any given color value, what are the different set of colors that are perceptually the same? And so to answer that question, we performed psychophysical experiments. Here you can see a user that is wearing a VR headset, and the screen in front of the user actually mirrors what the user is seeing. And we asked the user to fixate on the cross at the center of the screen. which is not quite visible in this one, but there is a crossover there. And then we placed 4 different disks at a given eccentricity 10 degree in this example. And out of those 4, 3 are reference colors, which are identical, and 4th one is a test color. So during the experiment, we start with a test color, which is very different from the reference. And slowly, step by step, we make the test color more similar to the reference. And whenever we change the test color, we actually ask users whether they were able to tell any difference between the test and the reference or not. So when we reach the point where users can't discriminate between the test and the reference, that's when we know we have reached the discrimination threshold on that particular axis. And then we repeat that the same experiment on the different axes to get discrimination regions, the complete discrimination region, basically. And here's how the result from the study looks like for one user for discrimination disks placed at 10 degrees centricity. The black marker in this image is the reference color, and the red markers around those around them are the discrimination threshold that we observe for that particular user. And here, and so all the color values within one discrimination regions are perceptually the same. And here's actually results for 2 other users. You'll see that there are differences in the discrimination region. This is because everybody perceives colors differently. Now, if you look at results for other eccentricities, 25 degree and 35 degree, you will see that the shape of the discrimination region is largely the same. The size increases, which is understandable because visual acuity decreases as you move further away from the foveated region. Now, once we collected all the data from the experiments, we actually regress these elliptical regions around the reference colors. The reason we regress ellipses is because classical psychophysical experiments suggest that the discrimination region is elliptical in shape. Now, of course, we can't perform the experiment for all the sRGB values and for all the given eccentricities for human vision. What we need is a model which for any given sRGB value and any given eccentricity can predict the parameters of the ellipsoid. And so using the data that we collected from the experiment, we trained a tiny neural network which can predict, which can do the prediction for us. And here's how the ellipsoids actually look like for a 10-degree eccentricity. Now, one thing to notice here is that you can span the entire sRGB space using just a few colors, the ellipsoids of just a few colors. And so you don't need to encode all the different colors in the sRGB space, which is what inspired our compression algorithm, which I'm going to talk about next. So actually, before talking about the perception-driven frame buffer, I'll give you a brief overview of how compression works in existing hardware. So whenever the GPU produces a frame, it goes through an encode block, which compresses the frame and writes it to the frame buffer, which is in the main memory. From there, the display controller reads the frame, unpacks it, and sends it to the display. Now, the real-time frame buffer compressions work by selecting a base color in any given tile, and then it subtracts that base color from all the other color values to get the deltas. The idea here is that the deltas are much smaller than the original color values, and so you don't need that many bits to store them. This is actually how many bits you would require to store the delta values. And it depends on the difference between the min and the max. And so the compression rate that you get out of this algorithm actually depends on the worst case. And in this example, the worst case is highlighted in green. As you can see, the difference between the min and the max is still quite high. So in this work, our intuition is that we can change the different color values in a given tile such that they're more similar to each other. And in doing so, we can reduce the difference between the min and the max, and also the number of bits that are required to store the deltas. Now, the rigorous mathematical way to do this compression is to formulate it as a constraint optimization, where the objective function is to minimize the number of bits, and the constraint is that the resulting color values are within the discrimination region. But this optimization problem is non-convex, and no solvers can actually solve them in real time. And so it's not amenable for real-time frame buffer compression. And so to solve this, we went back and looked at the structure of the ellipsoids, and we make two different observations. First is that the ellipsoids are elongated along the blue axis and the red axis, and not so much along the green, which is because human eyes are more sensitive to change than green color. So what this gives us is we have more wiggle room to change the colors along the blue and the red axis. And it turns out that we can get decent compression rate by changing the color value along just one axis. For example, the blue axis as shown here. And so using that heuristic, we can modify the non-convex optimization problem to a convex optimization problem, which also has an analytical solution. You can actually refer to the paper for proof of convexity and a detailed analytical solution. In this presentation, I'm only going to give an intuition, which is that for all the ellipsoids in a given tile, we want to find a threshold where we can move all the color values to. And so we calculate these highest lowest points and the lowest highest points. And then we collapse all the color values to those two planes. So we actually have a software implementation of this algorithm running on a MetaQuest Pro on the mobile GPU. But because the computation is intense, so we couldn't get more than 1 to 2 frames per second out of it. And so we propose our own accelerator, which can actually run on a Xilinx Sync FPGA at 140 frames per second. So this is how the accelerator works. So we propose this color adjustment units, which sits between the GPU and the original base delta encoding, which I presented earlier. The color adjustment unit has multiple processing elements. Each processing element is responsible for changing the color values in one tile. And each processing element would actually change the color value along both red and the blue axis and select the best one of them. Each processing element also has a pending buffer associated with it. So this pending buffer actually stores the incoming pixel values and the discrimination region ellipsoid parameters that the GPU produces. And the dimension adjustment unit implements the digital logic for our compression algorithm. So here's how the output from the compression algorithm actually looks like. On the left, you have the uncompressed scene, and on the right, you have the compressed version of the same. They're virtually the same, and it's quite literally impossible to tell them apart. We also have an end-to-end pipeline working on a Xilinx FPGA. And so here you can see a user testing it out on a mobile display, which is connected to the Xilinx FPGA via HDMI, and the screen in front of the user mirrors what the user is seeing on the mobile display. And the user here is my lab mate, Vijay, who actually had built this end-to-end pipeline. If you want to test this pipeline out for yourself and play around with it, you can check it out using this GitHub link. Now I will talk about results. So first is bandwidth reduction. On the x-axis, we have 6 different scenes. These are actually 360-degree surround scenes that we tested with. And on the y-axis, we have bandwidth reduction over the baseline. We tested 3 different baselines for this evaluation. First was no compression, which is uncompressed image, and we can reduce the bandwidth by up to 75% over that. The second one is base delta encoding, which I presented earlier, and we can reduce the bandwidth by up to 18% over base delta. And the third one is PNG, and we find that our compression algorithm can beat PNG in 3 out of the 6 test cases. Now, the important thing to note here is that PNG is an offline compression algorithm and cannot be performed in real time on the hardware. And so it's not quite feasible to use this for real-time compression. Next is power saving. To estimate power saving, we tested with 4 different frame rates and 2 different resolutions. So these are the configurations that MetaQuest devices support. And on the y-axis here is the overall power saving, accounting for any overhead that the accelerator adds. And we can save anywhere between 180 milliwatts to 540 milliwatts of overall power. We also performed a user study to test the effectiveness of our compression algorithm, where we had 11 different participants from different age groups. And On the y-axis here shows the number of participants who could not tell the difference between a compressed and an uncompressed scene. And as you can see, most users actually couldn't tell them apart. Now, just to summarize the talk, memory traffic actually adds a lot of power overhead, especially in VR devices. And so we are proposing a frame buffer compression algorithm that leverages human color perception to get better compression rates. And we are proposing a hardware accelerator for the same, which can run in real time on an FPGA. And we can reduce the bandwidth by up to 74%. And we can reduce the power by up to 540 milliwatts. Thank you. And I'll take any questions.
All right, I think we have time for one quick question. And is our next speaker here? Yeah. All right, come go ahead and come set up. So I had a question while he's setting up. So it seems like this design assumes that the user is looking sort of straight ahead or like at a fixed point. Does your design sort of respond to eye movement, and what's sort of the latency to reconfigure?
Yes, most modern VR devices have the eye tracking hardware, and they can actually tell actively where the user is looking at. And we can utilize that and apply the compression algorithm based on that. So we don't apply the compression algorithm in the foveated region, just in the periphery.
I see. Yeah. And so it's fairly instantaneous to change which part of the image is the periphery. Yeah. Okay, awesome. Thank you. All right, well, our next speaker is Nuntipat Narkthong, and I'll just let him take it away. Tell us about what you've been working on.
Thank you. Hi, everyone. My name is Nantipat from Northeastern University. Today, I will introduce MicroVSA, an ultra-lightweight vector symbolic architecture-based classifier library for always-on inference on tiny microcontrollers. In summary, MicroVSA is a tinyML inference libraries for microcontrollers. We support the tiniest 8-bit to the very high performance 32-bit MCU. MicroVSA support binary vector symbolic architectures or VSA-based classifiers model. It has been tested on 10 MCU and 6 datasets. It has extremely low memory utilizations. We talk about around 10 bytes for binary classifiers. And compared to an unoptimized implementations, we achieve up to 23.8 times speedup and 16.2% accuracy improvement. I would like to start by giving some background about the binary VSA classifiers. So in short, there are two main steps during binary VSA inference. First, the input is encoded into a sample vector S. Then we perform similarity measurement between S and all class vectors C1 to Cm. The prediction label is the argmax of the similarity value between S and all class vectors. Note that the two main operations are bitwise exclusive OR and bit accumulations, making this algorithm very efficient on ASIC and FPGA. However, there are a few challenges to implement this algorithm in commercial MCU, which are used to build many edge and IoT devices nowadays. First, the native implementation style using a byte array to store a binary vector is best in efficiency, but the computation is simple as the exclusive OR and addition are supported in the MCU ISA. On the other hand, using only one bit to store each element in the vector is efficient in terms of space and allow for parallel computation as multiple bits can be exclusive OR at the same time. However, this implementation is slow due to the lack of machine instruction for bit accumulation in all current MCU ISA. The interesting question is, how can we achieve both space and time efficiency on the MCU? To address this problem, we propose a new VSA algorithms called MCU Optimized LDC. The key idea is to remove the immediate binarization step and merge the encoding and similarity measurements into a single step. Now, the similarity value P can be computed as a summation of the pop count of the V exclusive OR F and exclusive OR with C. For the detailed mathematical formulations, please refer to the section 3.2 in our papers. Compared to traditional binary VSA classifiers, our new algorithm achieve on average 4% higher accuracies for small model and 2.5% lower accuracy for large model size. Here we show a result for all vector length equal to 8 to 256. Looking at the FSDD model on the right-hand side, for example, we observe up to 16.2% accuracy improvement when the vector length is equal to 8 or the blue bar. And for most model, the accuracy improvement happen for all vector length up to 32 or 64, which are blue, orange, and green bar, and the red one in this plot. So in terms of the model size remain unchanged compared to the normal binary LDC. And in terms of number of operations, the efficiency of MCU optimized LDC depends on the word size of the MCU. In our benchmark, we found that the algorithm will be most efficient for up to 4, 8, and 11 class on 8, 16, and 32-bit MCU respectively. And this is confirmed by our benchmark result. For more information, please refer to table 7 in our papers. Besides the new algorithms, microVSA incorporates several other optimizations to achieve good performance on our model and MCU. First, we found that by changing the directions that we iterate through the vectors to perform computations, we can tailor the algorithms to fully utilize the CPU register and cache, if available on that CPU. The result of this optimization is shown in the row denoted as CR, CC, and RR in the following table. Overall, our benchmark show that we can get up to 2.6 times speed up on the same model, MCU, and compiler setting by just selecting the most optimized loop orders. Next, we look at the accumulator size. As it takes multiple instruction and CPU cycle to perform 16-bit and 32-bit addition on 8-bit MCU. And accumulation is done in the innermost loop, so it should be optimized if possible. Our solution is to partition the inner loop and accumulate a partial sum to a smaller 8-bit accumulators. With this approach, we achieve 1.15 to 1.65 times speed up, depending on the MCU architectures. Lastly, we look at the pop count operation, which is challenging, as there is no machine instruction to compute this in any ISA. On 8-bit MCU, a 256 entry lookup table can be used. But on the 16 and 32-bit MCU, additional instructions are needed as we need to perform multiple lookup for each byte in a word and to compile the result, negating the benefit. Negating the benefit of larger word size as shown in the number of operations in the table below. There are two solutions to these problems. First, we can use the known bit tweeting hack to compute pop count without using the lookup table at all. And even though the number of instructions is identical, this method doesn't perform memory load and could be faster than the lookup table as shown in the orange bar in the graph on the right-hand side. Alternatively, we can enlarge the lookup table to 11-bit. Or 248 entries, reducing the number of lookup from 4 to 3 in 32-bit controllers. And this size is still not too large to fit in the RAM of most MCU. In our test, using 11-bit lookup table provide up to 1.55 times speed up compared to the bit tweeting method. And the result for the larger lookup table is the green bar in the plot. Compared to traditional classifiers such as a decision tree and random forest, microVSA achieve up to 5% higher accuracy than the random forest classifiers while being 11 times smaller. However, our runtime is slower at around 10 milliseconds, depending on the model size. Note that we only consider model that could fit in an 8-bit MCU with 32 kilobyte of flash and 2 kilobyte of RAM, such as the Arduino Uno in this benchmark. For full result, please refer to the table 6 and 7 and figure 11 in our papers. On the other hand, comparing to the tiny CNN model, microVSA achieved comparable accuracies while using 7 times less flash and 116 times less RAM. In terms of runtime, both CNN and ARM model run in a few microseconds on the modern ARM Cortex M4 MCU. For full results, please refer to table 9 in our papers. In conclusion, these papers present microVSA and optimize VSA-based classifier library for all microcontrollers. We propose a novel MCU-optimized LTC algorithms and several optimization techniques for different MCU architectures. We evaluate microVSA on 10 MCU, representing 9 instruction set and 6 data set. We think that this study suggests that VSA is one of the promising directions to further reduce the cost and powers of machine learning on the edge. For more detail, please check our papers and our code in GitHub. Thank you, and I'm happy to take any questions.
All right, any questions for our speaker? I was wondering if you could comment on, does this generalize beyond MCUs? So for instance, if I have these bitwise instructions you were mentioning that are lacking, is this still a useful technique?
Actually, this work is not, as you said, it's not limited to the MCU, of course, and it can be used on the normal CPU as well, although it is really fast, and this model is really tiny, so it will be run real fast on the modern laptops. So the optimization might not be that necessary, but on the really tiny MCU, and that could make a lot of difference.
Does it actually run faster than a CNN for the same task on a laptop, or have you measured it?
For the runtime compared to the CNN, it is really identical. So so it is the rightmost bar. So in the first model, the with the M data set, our runtime is actually 10 times faster, but on the other data set, our runtime is 1.85 times lower. So it just depends on the architecture of the CNN. But for all of the model, it is still just 1 or 2 milliseconds, so not much. Even though it's 10 times, it is just 0.2 millisecond and 2 milliseconds, so not so both are still real fast.
Right. I mean, I could also see the case for the space efficiency, just fitting in caches better.
But for the flash and RAM, this is when our solution make a lot of difference, around 100 times less flash and 10 times less. I think 100 times less RAM and 10 times less flash than the CNN.
Be sure to say where you're from, your name, where you're from.
Thanks for a great talk. Zishen from Georgia Tech. I have a quick a question on the overhead. So I guess for this micro VSA, you need to encode the image to vectors, but for the CNN, you do not need to encode. So could you comment on the overhead of this encoding?
So actually, as you said, for the micro VSA, we need to encode the input pixels to the vectors, but all the runtime and already include this encoding step. So I think it should be a fair comparison.
Thank you.
All right, let's thank our speaker.
Thank you.
As he's setting up, our final speaker for the session is Harrison Williams, from a recent PhD graduate from Virginia Tech. He is on the job market for academic and industry jobs. So when you're invariably wowed 15 minutes from now, he will be courting offers. I also wanted to just express some appreciation to all of our speakers for the hard work that it takes to compress an informative talk into about 12 minutes, right? It's been my experience that the difficulty of talk preparation is inversely proportional to the length. So thank you very much. With no further ado, let's listen to what Harrison has to teach us.
All right, well, thank you for the introduction. I'm going to talk today about our work on energy buffering in batteryless systems. This is a collaboration with my advisor, Matthew Hicks at Virginia Tech. So this work targets mobile and IoT scale energy harvesting sensor systems, which replace the batteries that are typically bulky and lifetime limited and often volatile with energy harvesting circuits, which now enable the systems built around them to be smaller, operate for longer, and be deployed in environments where the volatility of batteries is unacceptable. Basic batteryless systems use an energy harvester and a buffer capacitor in the sort of basic operating mode where the harvester slowly charges the capacitor until it reaches some enable voltage, and the system discharges the capacitor in a brief burst of operation. Now, naturally, the size of the capacitor is chosen at hardware design time, and it's driven by system requirements, which can often change throughout the application. Sometimes we want the system to rapidly charge to our enable voltage so that we can begin low power operations like sensor readings. So this lends itself to a smaller capacitor. Other times we want to buffer more energy for a continuous burst of operation to reduce software overhead recovering from restarts or to support high energy atomic operations like radio transmissions. This lends itself to a larger capacitor. And so these things exist on a trade space. And unfortunately, with single capacitor systems, rapid charge time and high capacity are mutually exclusive. Making problems worse, in a lot of the real-world deployments that we expect batteryless systems to really hit their stride in, input power is highly volatile, often looks something like the plot here on the right. A lot of the input energy is concentrated in these brief bursts of high power energy input, and we need high capacity to capture these power spikes without hitting our overvoltage limit, which in a smaller capacitor system might force us to burn some of this energy off as heat. So we need capacity to capture these power spikes without compromising charge time. So there's some state-of-the-art work that does address this through the idea of what I call capacitor multiplexing. We have a system here on the left where system designers can choose between different size capacitors as they go throughout their program. So we have our sense and compute application here on the right. For our actual sensing system, we might want to switch to our small capacitor to allow the system to enable rapidly. When we move over to actually transmit these samples, we can switch over to our larger capacitor to buffer a lot of energy for the radio transmission. So systems can operate at different points in the charge time capacity trade space. Unfortunately, it turns out that energy gets fragmented across these capacitors depending on the input of or depending on the shape of the power input. So we have a simple toy example here with two different size capacitors multiplexed together and an average power input of 1/4 milliwatt. If we charge our small capacitor first, we get the basic batteryless mode of operation where we charge and discharge this capacitor and get about 30 seconds of on time. Unfortunately, if we concentrate that power in a brief power spike at the beginning of our trace, what happens is that we charge our small capacitor up to the overvoltage limit and redirect all of our incoming energy to the larger capacitor. Eventually, our power spike ends and we run exclusively off our small capacitor down to the lower limit of our system. Once this happens, we have energy fragmented across capacitors, so it's the same amount of energy, but at voltages that are too low for us to take advantage of. And the end-to-end result is that our total on time has been reduced by a factor of about 2. The only thing that happened was we changed the shape of our power input. Beyond performance, this energy fragmentation can also complicate design. So if we imagine refactoring our software to this more event-driven model shown here on the right, it becomes less clear which capacitor I should charge first because I don't know which event's going to happen first. If I make that decision and then later decide that I want to use my harvested energy for a different event, I can't do that because I can't move energy between capacitors. I have to allocate energy at harvest time to a specific task that I predict is going to happen sometime in the future. I can say more formally that energy isn't fungible in a system like this. So this lays out the sort of problem statement that we try to approach in this work. We have a charge time capacity trade space that we would like to eliminate using a unified energy interface that provides fast charge time, that is system level reactivity, and arbitrarily high capacity while also maintaining energy fungibility. We'd also like to do all of the above without burdening the programmer to think about energy input. So this means that we need a system that automatically expands and contracts capacitance according to the stored energy. The most intuitive way to do this is to have one common supply rail that I just add and remove capacitance from. So if we have one capacitor here that we charge up to some upper voltage, and connect another capacitor to it, we've increased our capacitance, but unfortunately what happens is that current flows from the charged capacitor to the discharged one to equalize their voltage. And it turns out that 50% of the energy that I have buffered in the system is lost in resistive heating from the current spike, equalizing the voltage between the capacitors. So we pay a very high price to increase capacitance in the system. When we decrease capacitance in the system, we also pay a price because any energy that we put on that capacitor is lost. We can no longer access it, and it's eventually going to be lost to leakage. To overcome this, we borrow a circuit from the world of power electronics called a charge pump, where the actual implementation is shown here on the upper left, and the equivalent circuit is on the bottom left. So in this configuration, our two capacitors are in a series configuration with an equivalent capacitance of C/2. That means with a relatively low amount of energy, we can charge up to our enable voltage and begin operations. We've achieved our high reactivity and short charge time. Once we reach capacity and we want to buffer more energy, say for a high energy power spike, we can throw our switches into the opposite configuration, which multiplies our capacitance by a factor of 4 for an equivalent capacitance of 2C, and cuts our voltage in half, so we can continue harvesting more energy. So we've realized variable capacitance and voltage without energy loss. If I'm at a high capacity operating point and I want to reduce my capacitance, I can go in the opposite direction, throwing my parallel mode capacitors back into series, which reduces my capacitance by a factor of 4 and also doubles my voltage, so I can continue extracting power from this buffer. So we can extract a lot more energy from this system than we can from a simple system where we just disconnect the capacitors. So this charge pump architecture forms the foundation of our approach that we call React. We have a set of capacitor banks connected in parallel to a common rail so that we have arbitrarily high capacity. And each capacitor bank contains these capacitors organized in this charge pump configuration. We add a software interface for capacitance control from the microcontroller. We add a small decoupling capacitor to smooth switching voltage spikes when we change the voltage and capacitance in these charge pumps. And we add isolation diodes to prevent interbank current, so that current doesn't flow between the banks, which would cause that dissipative loss that I talked about earlier. So this is the high-level overview of our unified reconfigurable capacitor architecture that provides fast charge and high capacity, fungible energy storage, and as we'll see later, a transparent software interface. Basic overview of how it runs: from a cold start with no energy in the system, energy flows directly from the harvester to the small decoupling capacitor. And because the capacitor is by design small, we rapidly reach our enable voltage. If we need to buffer more energy and we reach capacity with the small capacitor, we can attach one of our capacitor banks initially connected in the series configuration. So we don't see a big voltage drop because we're adding relatively little capacitance. Eventually, if we need to continue buffering more energy, we can reconfigure that series bank into a parallel mode to add capacitance without any sort of energy overhead. And we can continue doing this with as many capacitor banks as we have, adding them sequentially in series mode and then in parallel mode. When we're discharging these capacitor banks, we can go in the opposite direction, reconfiguring banks from the parallel mode into series to boost their voltage and extract the most energy we can from them before we disconnect them from the common rail. So we implement and evaluate React in full hardware systems shown here on the right, supplying an MSP430 low power microcontroller, which is common in these batteryless systems, using 4 dynamic banks in addition to our small static capacitor. We evaluate the system on real energy harvesting traces using a replay system that we developed for repeatable experimentation, using both solar power and RF power traces gathered both by us and other researchers in the community. We evaluate on a set of benchmarks ranging reactivity and capacity-bound workloads, sensing, computing, and networking applications that we would typically find on these batteryless systems. And we compare it to a set of baseline systems representative of the state-of-the-art 3 single capacitor systems and similar work in the world of dynamic capacitance called MulBERRY, shown here on the bottom left, that also takes advantage of the charge pump architecture that we explore, but uses a fully interconnected network of capacitors. So this gives them a very wide range of capacitance configurations, but reintroduces the problem of dissipative power loss, because every time I reconfigure this capacitor array, capacitors at different voltages are going to be connected and current will flow between them. We'll see that ultimately this reduces their performance down to below that of even static capacitors. The first part of our evaluation is this plot here on the right, which shows the buffer voltage for React and a couple of our baseline systems over the course of a typical batteryless deployment, with the bars on the top showing when the system is actually operating. show that React reaches operational voltage on average 8 times faster than an equivalent capacity static system, but also runs for 40% longer than an equally reactive static system because it never needs to burn off energy due to overvoltage using a too small capacitor. Compared to prior dynamic capacitance approaches, React eliminates the switching dissipation that plagues prior approaches, wasting energy during their dynamic behavior to bring their performance down to below that of static capacitors. Averaged across all of our benchmarks and all of our evaluation scenarios, we see that React realizes, like I said, an average 40% performance improvement over systems that are equally reactive, a 20% performance improvement over the next best operating static capacitor system, and a 26% performance improvement over prior dynamic capacitance works. So that's the performance side. On the programming interface side, React also simplifies the programmer's job. Because energy isn't fragmented across different capacitors, the programmer doesn't need to worry about where they put energy when it was gathered. It offers a unified fungible energy interface that simplifies programming. It's easy to see how we can build an event-driven model here on the right. All we need to do is augment our event-driven code with code to pull the current energy state of React to see if it's above or below the energy cost of our upcoming event. The result is that on benchmarks with competing reactivity and capacity requirements, React realizes a 54% performance improvement over the baseline. So in summary, we demonstrate that batteryless systems face competing performance requirements that render static capacitors insufficient for the job. Prior approaches either fragment energy and complicate system design or face significant energy overheads from dissipative power loss. And we introduce a circuit called React, which eliminates the charge time and capacity trade-off and efficiently combines energy in a unified variable capacitance buffer. And the result is an intuitive programming interface and performant intermittent execution model decoupled from the volatile power front end. So for more details, I invite you to look at our paper. We open source all of our hardware and software artifacts at the GitHub link below, and I'm open to questions. Thank you.
All right, any questions for our speaker?
Hi, thanks for the talk. I'm Harsh from Carnegie Mellon. My question is like, how accurate does your model of how much energy each task is going to consume need to be for your React system?
Sure. So we consider that to be sort of orthogonal. It's a difficult problem on its own because, you know, tasks can have data dependent energy consumption.
Right.
And so that's something that we would imagine being combined with React. In our actual evaluation, we just do sort of ad hoc because we're running individual benchmarks and we know what the power consumption is going to be because it's the same every time.
Mm-hmm.
So for our purposes, because we're really evaluating the efficiency of the circuit,
mm-hmm.
we do a sort of a search of minimum capacitance to effectively finish a an atomic energy operation, if that makes sense.
I see. Is there a way you can extend your system design to be dynamically tracking how much energy it's consuming and then expanding the capacity on requirement?
Yeah, and so there's work on that because that's just for these batteryless systems, that's a generally useful feature to have.
Mm-hmm.
So it's not something that we explored with this, again, because we're focusing on the buffer behavior, but it's definitely an interesting direction to go, especially because of the way that the React software interface would interact with that sort of information. But yeah, looking into at the actual software benchmarks, that's not something we explored for this work.
Sounds good. Thank you.
So when you said fragmentation, I've done a lot of work in file systems and my ears popped up thinking about space fragmentation. And one of the things I know, if I understood your talk correctly, as you sort of grow the capacity of the system, it's sort of the same amount of capacity each time. Is that correct? With space, a lot of times you want to like double the amount you add each time. Would that make sense in your system, or would there be benefits or drawbacks?
So actually, it's something I glossed over in the presentation, but in our actual implementation, we do something very similar to that. You want to sort of control the amount of capacitance you add to the system, because if you add too much, you can actually have all of your energy going into the capacitance that you just added. The system will eventually shut off because you're still charging up that large capacitance. And so in our implementation, we actually do very similar to what you describe, where our first bank adds, say, 100 millifarads, second bank adds, another 100 millifarads, but bank 3 adds maybe 500, bank 4 adds 1,000. So yeah, that is
Gotcha.
something that we.
So
we
there may be
explore.
some downs, if I'm understanding you correctly, like there may be some downsides to just full, like, quadratic growth, right? So it's
Yeah.
not that aggressive, but you're doing something very
Yeah,
similar.
yeah, exactly.
Cool. All right. Well, I think that's about our time. Let's thank our speakers once again. And thank you all for completing the ASPLOS 2024 orienteering course. And with that, I think we have a break back over, in somewhere in North San Diego. Yeah, there's. I understand the